morning to all of you. Okay, last lecture we have seen the concept of stress and strain. Today we will going on the next page, Poissons ratio. What is meant by Poissons ratio? Poissons ratio is nothing but when the homogeneous material is loaded within the elastic limit, then the ratio of stress to the strain is constant. It is known as a Poissons ratio. Okay, what is meant by Poissons ratio? When the material is loaded within the elastic limit. Means here we have seen the two concepts, right? First is a elasticity. What is the elasticity? When material is regains its original size and shape after removal of the load, it is called as a elasticity. Okay, and what is the plasticity? When if the material does not regains its original size and shape, it is known after removing of the load is known as a plasticity. I have given the example of the rubber. When you stretch or apply the external forces on the rubber, okay, and when you remove the load on that rubber, you will get original shape and size. Okay, come to the point. What is the homogeneous material again? There is a uniform. You will get the property of that material. Uniform property of that material. Okay, or we can say the Poissons ratio. It is the ratio of lateral strain to the linear strain. Lateral strain to linear strain. Again, what is the lateral strain? We have seen the both things, lateral strain and linear strain. Okay. This Poissons ratio is denoted by mu or 1 by m. Okay, we are using the both notation. It is denoted by the mu or 1 by m. Okay, and see, I will write the formula of Poissons ratio. Mu or 1 by m is equal to what? It is the ratio of lateral strain is denoted by EL and linear strain is denoted by the small e, known as a Poissons ratio. Okay, we'll give you here one small example. We'll consider one cylinder. We'll consider here one cylinder having the length L and diameter D. Having the length L, we will take the section of that cylinder. See, consider the length of that cylinder is a capital L, and what is the diameter? D is there, small d. I will consider the diameter of the cylinder is a small d. When you are applying the pull force or push force, okay, vice versa. See, if you are applying, I will apply here the pull force on the given cylinder. Then what happens when you are applying the pull force? Then this dimension will be increased. Okay, then dimension will be increased. And what about the diameter? Diameter will be decreased. Then which is the lateral dimension and which is the linear dimension? This one is a delta L, and also this one you will get the change in length delta L, and this one is a change in diameter delta D is there. Okay, which is the lateral dimension and which is the linear dimension? Okay, what is the okay, see here which is the linear dimension? I will write here mu is equal to, first see the lateral dimension. Lateral dimension is a, here we will get this dimension is a compressed. when you apply the full force on the given cylinder, then this will be length will be increased and diameter will be reduced. Diameter will be reduced. Then in this way we'll get mu is equal to lateral dimension is the change in diameter upon denoted by original diameter divided by linear dimension is delta L divided by L is there. Delta L divided by L is there, and this will get the negative because this lateral dimension will be compressed. That's why we are using here negative symbol. Okay, we'll reduce the diameter. Okay, another way, all of you getting mu is equal to what is the linear EL is equal to, you will get the minus delta D divided by D, and this one linear strength you will get the delta L divided by L. Okay, if you have considered the rectangular block, you can see if you have considered here one rectangular block having the dimension LBT. Okay, length of this block is L, width of this block is B, and T is the thickness of the block. And if you are acting the external force P on the given component, then what happened here in the linear which is the linear dimension? Okay, in the direction of applied force. Which direction we are applying force? L direction or X direction we can say. Then you will get the linear strength is equal to, here is there, you will get the delta L divided by L is there. Delta L divided by L is there. And what is the lateral dimension of that component? Lateral strength is equal to, already we have seen, the force is applied in the right angle. The force is applied in the right angle to the applied force, in the direction of the applied force. It is known as a lateral strength. It is denoted by the EL. Then again see, here is a two dimension. When you are applying the force in the longitudinal direction, then this B and T will be reduced. Then we will get minus delta B divided by original B, or minus delta T divided by T. Okay, minus. Why minus? Because of here you will get the compression. If you have seen in the theoretically this value of the Poissons ratio is given minus 1 to 0.5. And if you have seen the practically this value we will get in between 0 to 0.4, 0 to 0.2 to 0.4. Most of the metal having the Poissons ratio in between 0.25 to 0.34. Okay, most of the metal will get the value of the Poissons ratio is 0.25 to 0.34. Okay, see, rubber having maximum Poissons ratio is equal to 0.49. All of you getting what is the Poissons ratio? Okay, what is the application of that? You have to remember the definition. It is the ratio of lateral strength to the linear strength is constant, and the material is coupled within the elastic limit. Okay, then next is we will going on the Hooke's law. Okay, all of you getting the Poissons ratio? Next is the Hooke's law. What is the Hooke's law? Okay, we have seen the stress-strain graph, right? Stress versus strain graph for the ductile material as well as brittle material. Okay, there first point we have seen the Hooke's law. Right? Hooke's law is obeyed in the first point. Hooke's law. This is the name of the scientist. Okay. Hooke's is the name of the scientist. Okay, we'll see the details. Hooke's law. Hooke's law, when the material is loaded up to the proportional limit, then the ratio of stress to the strain is constant. Is known as a Hooke's law. When the material is loaded up to the proportional limit, then the ratio of stress to the strain is constant. Stress to the strain is constant. Is known as the ratio of, we can say stress is directly proportional to the strain. Stress is directly proportional to the strain. Then we can write sigma is equal to constant into E, or you will get the relation constant is equal to sigma divided by E. Okay, there in different books for the different application this constant value is different as per the dimension of that material, then the size of that material. Okay, again we can say the stiffness of that material. This you will get the constant value is different. I will draw here one graph. See, we'll explain with the help of that graph. Here is the strain is denoted by the E and stress is denoted by the sigma. Stress versus strain graph. In that, see why stress is directly proportional to the strain. You draw. If you have taken any point, then see this value will get same. This value is you will get the same. That's why stress is directly proportional to the strain. Stress is directly proportional to the strain. If you have taken the example of that spring, say you know the spring. We'll take the example of the spring. See, this is the unstretched spring is there. Okay, unstretched spring is there. Then I will draw another one. This one is a fixed. Okay, and in the second part, we have attached some mass to that spring, and here we will get the deformation force F. Deformation force F. You know that this F is equal to mg. What is mass of that spring into the gravitational force? You will get the force is equal to mass of that spring into gravitational force. See, here is a unstretched spring is there. We are not applying the mass, but here when you apply the mass, then this spring will be extended. Okay, this spring is extended from its original position, and we will get the again changing length of that spring is a delta L. Again I will draw, if you are acting again here more mass, then this will be again extend more than this spring. Okay, I will act here 2m mass. Okay, then again here is a force is there. Again you will get the more than that deformation in that spring. In that spring here is a, again you will get the more deformation. This L plus delta L deformation you will get. This is the original length of the spring, and this delta L is the deformation of the spring. Okay, then see again here what I said, stress is directly proportional to the strain. Here is a force is directly proportional to the elongation. Elongation we can say the x. Force is directly proportional to the elongation. Elongation of that spring. Here is a deformation force is there. Again see I will write here F is equal to K into X. What is this K? K is the constant. K is the constant. This is depend on the dimension of the material, and stiffness of the material, or we can say the size and shape of that material. Each material having different constant value. Okay, you will get the different constant value. Okay, or sometimes we can write F is equal to minus kx. Why minus? If you are acting the mass m, okay, the spring is elongated, and sometimes what happen? We'll get the resisting force inside that spring. That's why minus. They are resist. We have seen in the first lecture resistance force, right? That's why we are applying the minus because of compression. Similar way, here we are applying this constant is denoted by the E. E is equal to sigma by E. What is the E? E is the Young's modulus. Young's modulus. It is also known as a modulus of elasticity. Modulus of elasticity. When the material is loaded within the elastic limit, then the ratio of stress to the strain is constant, is known as a modulus of elasticity, and it is denoted by the capital E. Okay, and unit is a Newton per mm square, or Newton per meter square, or Newton per meter square. Then see, we will write here E is equal to sigma by E. We will get the one relation. See, I will write here E is equal to, what is the sigma? Sigma is the stress, is nothing but P by A. And what is the E? E is the change in length upon original length. Then if you want to find out the elongation in the spring or elongation in the any component, then how to calculate that elongation? You will get the new relation. See, delta L is equal to PL upon A. When you solving the numericals, then this is very important formula. See, delta L is equal to PL upon A. You will get this value in mm, meter or centimeter. Okay, length unit is a meter, centimeter or mm. Okay, how do you get it? This is very important. Now the Hooke's law, then Poissons ratio, then modulus of elasticity. Today we will stop here.